I hope you guys will enjoy it. It'll take about half an hour, and after that, there's some questions you can ask all you want. And here's the quick little outline. I will go over how the steam injection and extraction works, and talk about some of the challenging things, including the pressure cycling, why we're doing it, why it's critical, some limitations of the technology, so it isn't all about how great it is, about lower permeability zones and fractured rock creating challenges for the steam, and then how we have combined steam injection with other thermal technologies such as conductive heating and electrical resistance heating to address more complex sites. At the end, there'll be the question and answer session. A little quick summary of who I am. I am from Technical University of Denmark and took my master's thesis and PhD in engineering there from '94. Then I was lucky enough to get a postdoc project in Ada, Oklahoma at the Kerr Research Lab, studying basically TCE, PCE behavior when you heat the subsurface. Then from 1999 until 2004, I was at SteamTech. I actually skipped over almost the most important phase at UC Berkeley here. I was up there with Ken Udell and learning from him in the laboratory and in the field, how to apply steam in the field. Did that in SteamTech for about 5 years, and since 2004, I've been with TerraTherm as the Chief Technology Officer. And the focus of what I've been doing has mostly been starting with understanding how this stuff all works on paper and in the laboratory, and then go to the field and apply the steam-enhanced extraction, and later on combining it with other thermal technologies. And before I knew how to do anything, this site in Visalia Pole Yard was already under remediation. This is a big Superfund site, 400,000 cubic yards, contaminated with creosote, NAPL to at least 140 feet below grade. And there was a group out there already doing this full scale. And to this date, this is still the largest thermally enhanced remediation system that I know of. We're beating it by just a few percent at the moment at Williams Air Force Base, but at this time in 1998, this was a very unique project, and they were able to use steam to extract roughly 160,000 gallons of DNAPL, or equivalent DNAPL. A lot of it came out in the vapor phase, but a lot of it also came out as NAPL, and the Superfund site was eventually delisted after 5 years past the steam project. They were able to turn off the pump and treat system, and the city of Visalia had their aquifer back, basically meeting drinking water standards at the property boundary. So at the time, it was just unheard of that this was even possible. And of course, I was very thrilled to learn from that project. And you see some of the most prominent people at the top here. Ken Udell, explaining the theory behind everything and really pushing this to work. Robin and Roger from Lawrence Livermore was strongly behind this project, and how also to monitor it during and know where the steam was going, and understand and help everybody and the EPA accept it. Hank Sowers from SteamTech provided a lot of the equipment, such as the steam generator that also destroyed the vapors at the same time. And Craig Eaker on the right from Southern California Edison was the corporate guy who took the chance and sold this to his company. This is a $25 million project, but at the end they were able to take a $80 million liability off the books, and he became basically a hero in the company from doing this. First time ever done, but very successfully, and these guys were behind it. So what they really did was they took oil field style technology, as you can see in a couple of these pictures at the bottom, and transferred them into environmental. And one of the things that you have to do is not just get 2/3 of the oil out like you do in enhanced oil recovery. You know, you have to get almost everything. So they basically took that leap and adapted the technology, but made the equipment work for it as well. One of the things with steam enhanced extraction and other thermal methods is that you have more than one mechanism. The first one, the most known one, is the vaporization, where you make the subsurface boil and the volatile chemicals such as PCE and TCE come out in the gas phase. And they do that because their vapor pressure increases exponentially, as you see on the left side, upper graph, and also the Henry's law constant increase dramatically. So both the NAPL and the dissolve phase is encouraged to go into the gas phase. And it happens at the pore scale, and steam is formed, and this steam flows out along with the volatilized chemicals. For steam enhanced extraction, that's not the only thing that happens. And another really important thing is the viscosity reduction of oils. As you can see on some of these graphs, the increased temperature leads to really big drops in the viscosity. And that is true for gasoline, diesel, but also even more so for the thicker oils, number 14 gravity oil, for instance, coal tar, MGP, L and D NAPL as well. You can go from hundreds of centistoke viscosity, which is really sticky, almost honey, to easily flowing NAPL as you see it accumulate in an oil water separator in the lower right there. So the oil can also be displaced in front of the steam because it becomes so much more fluid than when it's cold. And one of the things with steam illustrated here in a predictive modeling where we push steam from those two injection screens shown as red bars, is that the steam, the white zone, spreads from the different injection intervals. You can see a little tendency for it to rise above the injection interval, and over time it moves across and forms a steam zone with a condensate zone in front of it where you have the gray nuances. So that in that condensate zone, a lot of the mass is actually pushed in front of the steam and displaced towards the extraction wells. And it's not sufficient just to have vapor recovery. You also need liquid recovery, and you need to be able to get both the hot enriched water and the NAPL out of the ground when it approaches the extraction wells. Here's a typical steam well field. The spacing at this site in Pennsylvania that we did in TerraTherm was about 30 to 40 feet. So in contrast to other thermal sites that are maybe more common, ERH and conductive heating, where you have spacings of 15 to 20 feet, this spacing can be a lot larger at the steam projects when there's enough permeability to allow it. An injection well may look like this one that I show, with the steam coming from a boiler on the right-hand side through that black steam hose. It goes through the red pressure reducer, where it gets reduced to the injection pressure, typically at this site 20, 30 psi, compared to the up-gradient manifold pressure of about 100 psi. So pretty straightforward equipment. And then it goes through another steam hose just to make the connection easy, and then down the hole. So that's as simple a steam well as you can have out there. Some of the sites, including this one in Pennsylvania, has 2 injection intervals. Here's a 1-inch diameter one that was injecting 100 to 200 pounds per hour, and a 2-inch that was injecting a little higher flow rate. And we simply just picked them based on the flow rates and pressures that we need for the sites. You always need fuel to make steam, typically, and here's just an example of an oil tank and a boiler sitting in the container next to it. The boilers or steam generators are standard units that can be rented and brought to the site, and pretty simple technology now. So let's move to one example, nice old example, Alameda Point. It's good because it was very small, and it was easier there to basically understand how the technology worked than if you had a big area with a lot of wells overlapping. In this case, we had a small Ilnapple spill from a tank underground, and the outside of that spill is shown by this blue punctuated line. And that was the extent of it when we characterized it with the CPT membrane interface probe and laser-induced fluorescence, poked a whole lot of holes, and that was the extent of the Napple spill. After the Napple had been spilled, the motor oil, there was a TCE release as well, and the TCE was mixed in with the motor oil and still within the same footprint. So the remedy became a centrally located multi-phase extraction well, and then six nested steam injection wells around the outside. And you can probably guess that they're in the little corners of this hexagon. And the steam was injected up from the outside in, injected in clean locations outside the Napple and pushing inward towards the extraction well. You can see the steam generator in the upper left and the portable, if you will, effluent treatment equipment on the upper right. In cross-section, we put the multi-phase extraction well in the middle. As you can see here, the black curves show the laser-induced fluorescence footprint or signal. And you can see that the blue line, or grayish blue line, is the water table. You see that the oil in the middle was shallow, as well as down in the smear zone. But most of the site, the Napple was a little bit above the water table, and then 2, 3, 4 feet below. The approach was to inject steam in 2 intervals on the perimeter, an upper and a lower, and we injected steam in the upper layer so that we could sweep clean steam across the vadose zone, and so that when we volatilized chemicals from the saturated zone, instead of running up under the asphalt and condensing where it was colder, it would actually get swept by that clean steam in the upper zone. So we didn't really need 2 zones to get the site hot, but we needed the upper zone to sweep chemicals out so we didn't have a recontamination problem at the top. And here's some sketches of how it went with the 6 injection locations on the perimeter. We after 9 days have a little steam zone around each injection interval starting at the top, and you can see basically an example of how the injection wells work down there. No mass has come out yet. It's still cool in the middle. I'm going to move down a slide here. A couple of days later already, the steam zones were starting to overlap, so it happens pretty quickly with steam. Still cold in the middle, still no mass of significance has been extracted. But then a week or so later, we started to see hot water in the middle and oil in the hot water, as you can see here, trapped in a Teflon tubing. Napple started arriving with the condensation front, and shortly after there was steam breakthrough. So this was a very exciting day for us out there. So then the steam has broken through to the middle extraction well. You see in the cross section, it's hot in the vadose zone, and it's also getting hot down below. And at this time, we have extracted about 250 gallons of mass with the breakthrough. And you'll see in a moment that's about half of the mass that came out. Here we are, day 50, and we still have steam breakthrough. We've been doing pressure cycling, which I'll talk about in a moment, hot from the top down to basically the depth of the contamination. And we're up to about 500 gallons of Napple collected in addition to the vaporized contaminants. In the extracted groundwater, you can kind of get a signature of how well it's going and how far along you are. You can see here, especially the TCE, the upper graph, peaked at something close to 100,000 micrograms per liter, and then towards the end, when there wasn't much more Napple coming out and the site was really close to being clean, that concentration really dropped. So simply by grabbing samples of the water that the steam is flushing through there, you get a really good indication of whether you have a lot of mass lift. The other real good evidence is to take soil samples before and after. You see a chromatogram from a TPH analysis from before on the left and after on the right. And you'll notice that the lighter end hydrocarbons all the way up to about C16, so 16 carbon atoms, has been removed from the treated sample. And instead of having liquid flowable oil, as you see on the left, you basically, when you cooled this soil off, it was almost like an asphaltic material. There was still nasty looking dark stuff, but it was the heavier ends, and it wasn't soluble and mobile. So even at a boiling point of 100 degrees, which is what you'd achieve in situ with steam, you get chemicals removed that have boiling points of over 200 degrees. As naphthalene, for instance, C10 would have a boiling point of 214. It has been more or less completely removed at this temperature at only 100. Then the more risk-driving chemical TCE, which was, as I said before, dissolved in the oil, before and after in the groundwater, measured from multi-level samplers. You see here, and these are micrograms per liter. See, before we were at 71,000 in some points, and after the thermal treatment in the same multi-level sampler, that had been reduced to 62 micrograms per liter. That was like a month after the steam project. Then we came back 2 years later and redid this and found basically non-detect for TCE in all these same multi-level samplers. So there was definitely some microbial activity, and the leftover oil was probably the electron donor, and the site turned back anaerobic, and the TCE basically polished itself off, or the bacteria polished the TCE down to non-detect in a couple of years. We repeated the laser-induced fluorescence screening with the CPT rig afterwards to see if we had smeared the NAPL significantly. The red are the signals from before thermal, and the blue from after thermal. And you can see much lower signals after thermal, meaning that we had removed most of the mass. In a couple of locations, you may see a little bit of a downward smearing. If you look at the PC03, the blue line is slightly deeper. The peak is a little bit deeper, and that's probably due to the steam overriding the water, and then when we do pressure cycling, we have a little bit of slushing issue, if you will. So there could have been like a 1 or 2 foot smearing based basically on the steam zone being introduced. So nothing major, but just the only minor signal we have ever seen about having a little bit of a change of the bottom of a treatment zone in this case. So the lessons were you can basically remediate these small zones. We got 520 gallons of motor oil and starter solvent mixed together out. About 80% of the mass, 80% reduction in TPH when we sampled the soil afterwards. So 20% still left, but as I said before, the heavier ends and the less risky components of the motor oil were left. And for the volatiles, better than 99% reduction, and this is based on soil samples before and after. And then when a site is well enough characterized that you can inject steam on the clean perimeter, then that is a great way to do it, because you can basically corral the mass to the center, and that was how it worked at Alameda Point. Here's another example of a steam injection project at Guadalupe oil fields. We had 4 injection intervals there, and we were able to extract about 100,000 gallons of this diluent crude oil mix that they had spilled under the sand dunes. So just an example of a tremendous amount of mass coming out of a few wells, in this case 100,000 gallons over the period. One thing we learned there, was in sand dunes, so aeolian sands, and the anisotropy ratio there was like 2 to 1, so the vertical permeability was really high in addition to the horizontal. And we observed the steam was injected down in the treatment zone, and we saw it rise very readily in the vadose zone, which is above this line right here, if you can see my pointer. So we had a lot of the steam move up in the vadose zone, which was basically clean. The diluent was down here. And that was one of the reasons why, from a sustainability standpoint and other reasons, this is not the greatest full-scale application. When you have a very highly permeable vadose zone, and that's permeable in the vertical direction, it can be difficult to concentrate the heat with steam where you want it. So it was eventually decided not to go full scale. There were a lot of other reasons, but one of them is also the ecological impact in that very sensitive area in the California sand dunes. On the left, you see what it looked like before the pilot test. On the right, you see during the pilot test. And that type of alteration of the surface was not desirable either. So the 250-acre Napple plume is still there, and it was decided not to do it. That was probably decided before this pilot test, but we still did the pilot test and showed that you could get the mass out. There were just too many side effects. Another thing we deal with is the potential to create downward mobilization of solvents. This is a laboratory demonstration where we have TCE in the vadose zone, very highly concentrated, and steam is migrating from the left to the right. And where you see the dark red is the condensation zone. So the steam zone is to the left of there, and then it condenses, and the TCE accumulates, and then forms enough of a connected liquid phase that it actually, due to gravity, drains to the bottom of the vadose zone and goes down to the smear zone. So this is a condition you have to avoid in the real world. You know, you don't go into a vadose zone with high concentrations of DNAPL constituents and close your eyes and blow steam from one side to the other. Then you can actually create a groundwater problem that was not there to begin with. So we're always aware of that. One of the ways to fix it is the hot floor technology, where this is not what's shown in these slides, but where you would basically heat the bottom and make it so hot that the chemicals can't go through, that they would vaporize. Another way to minimize the risk of this is to co-inject air with the steam. So you basically have some blowers out there and the steam generator, and you mix the two before they go down whole. And the lower row of pictures here show that in a laboratory setting, starting again with a high Napple saturation in the sand here, and then you see the steam zone move across by that line, but air goes through the steam zone and carries the mass through and out on the right-hand side instead of it condensing. So you can calculate the proper air to steam ratio if you know the starting concentrations. And sometimes in the field we use this to minimize the risk of downward mobilization. Now comes maybe the more difficult to explain part of this, and that's why we use pressure cycling and how it works. We observe at these sites, and this is from the Young Rainy Star Center in Florida, we observe in the top graph the steam injection rate. When we turn the steam rate up and down in periods of 3 to 7 days, we see a huge response in the mass removal in the vapor phase that often correlates pretty well with these ups and downs. So, and it's counterintuitive. It is when you turn the steam down that you get the spike in the mass removal rate. So that's worth talking about, I think. Typically, it's the depressurization mode where your vapor phase concentrations peak. So what happens there is, you see on the left, in the pressurization mode, we're injecting steam at the higher rates and at the higher temperatures, and we are filling the steam zone, if you will, with steam at the highest temperature it can sustain at that depth, and it breaks through to the extraction wells, and the vapor lines are really hot, and that's your pressurized condition. On the graph on the top, you have moved the system up to a a pressure and a temperature that is in equilibrium. So those two correspond to each other. While you do that, you conduct heat into the overburden up above there. I'm assuming that it's a clay layer or something that doesn't take direct steam flow. Same thing happens at the bottom. You conduct heat in. This is not chemical movement. This is basically energy moving in. Then when you turn the steam down and on the right, you basically take the steam zone to a lower state of thermodynamics. You reduce the pressure by reducing the injection rate, and you drop it to another equilibrium temperature that's a little bit colder. So what happens now is that the top of the aquitard here has just gotten to a higher temperature and is now a little bit overpressurized, and has a little more energy than what it should have at equilibrium conditions. So it needs to get rid of energy, and the way it does that is that it boils some pore water, and that heat of vaporization of the water leads to that new equilibrium. So the arrows here basically indicate steam being generated by boiling pore water, and when that steam flows out, so does chemicals left in the top of the aquitard and at the bottom of the layer above if you have a confining layer. So this depressurization cycle, you're pulling mass out of the tight zones and you're sweeping it to the extraction wells. That's why you see a peak in the vapor recovery at that time. At the pore scale, it could look like this. If we're looking down in the top of a clay layer, you have a little mass trapped down there. When you depressurize, you make, just like when you take the cap off of a Coke bottle that has been shaken, all of a sudden you have another equilibrium, new pressure, and you need to outgas to get it to a new equilibrium, and that happens in the subsurface like this. The DNAPL starts to form bubbles, the groundwater boils a little bit, and you create a gas phase, and that gas phase is equal to a really big volume expansion on the order of 1,500-fold, and that gas goes up in the steam zone and sweeps to the extraction wells. So here's another example of us running into limitations when we thought we should use steam everywhere and it would be the silver bullet. Try it in granite, in fractured rock with not that many fractures. We did at Edwards Air Force Base. We had 3 injection intervals, as you see here in the middle, down to about 60 feet below grade, and we were trying to heat the area in between these outer multi-phase extraction wells and trying to heat and show that we could treat this TCE source zone above and below the water table. We really couldn't. We could get a lot of energy in the ground, but this is an electrical resistance tomography picture showing where it heated up, and it heated up very discreetly in the dominant fractures. Really not that surprising that the granite itself wouldn't take steam, but it also showed us that the fractures were not abundant enough to heat by conduction between the fractures in between them. So we actually had to give up getting the bottom 30 feet up to temperature, and we didn't do great with respect to reducing the TCE levels down there. We had 90% reduction in concentration, but that's not great when it's thermal. We want 99% or more for these type of chemicals. We were able to achieve that in the Vado zone a little bit later in the project, but never in the groundwater zone down below, where the steam was very discrete. Here's another example of a thermal model, and we're trying to heat a treatment zone to the red temperatures, which is over 98 degrees, I think it is. And then I have just tried to simulate groundwater flow across that treatment zone. And as you can see, if there's 1 gallon per minute flowing, you can still heat with an electrical method, no problem. If you have 5 gallons per minute, you see that the water on the upgradient side creates a cool spot. So in here, we're not able to overcome the cooling effect of the groundwater, and it's starting to carry some warm water off to the other side. And 10 gallons per minute is much worse. You'll have an untreated upgradient area, and you will have lost hydraulic containment and on the backside. This is if you're trying to do it just with an electrical method, and you shouldn't. So one use of steam-enhanced extraction in this case has been for us to inject steam on the upgradient side and prevent this cooling effect from happening, to partially to block the water, but also to preheat what might be flowing in. Other options for that, of course, is pumping or installing a barrier such as the sheet pile wall to stop this water flow, but steam can be used sometimes at a much lower cost to do the same. Here is a picture from a confidential site in Florida where we used conduction heating and steam together to address a site that had enough complexity that we couldn't have done it just with an electrical heating method. You see the conduction heater wellheads, if you will, here, 15 feet apart, and then here's an injection well for steam and a multi-phase extraction well over here, 30 feet apart, so double the distance. Again, that's possible with steam because steam can travel faster than the other media can. So the combination of the two was used, and it's easier to see in a cross-section. The reddish color indicates where we had high concentrations of solvents, and the green here is the clay interbedded unit, basically a clay layer, that had to be remediated to its base. The treatment zone went to the bottom of this clay layer in a couple of locations. Down here you have a sand, yellow-colored sand layer, and a decent hydraulic gradient. So if you were trying to heat this only electrically, then you would have too much groundwater flow and cooling in this zone below. You would not be able to get the bottom 3 to 5 feet of the clay hot enough, simply because that heat is getting carried away. So the solution was to use conductive heating from top to the base of this clay, and then inject steam at the bottom. We have steam injection wells here, and then multi-phase extraction wells. Create a little steam blanket underneath, and that way you can get to the proper treatment temperature in the bottom of the clay layer. And real data from the site here, temperature profiles. The clay layer went to roughly 40 feet depth, foot depth, and in those areas where we didn't inject steam, you see the temperatures like the punctuated lines here. That was the typical temperature profile we received. We don't get the bottom hot, and we did not get boiling temperatures at the base of the clay layer. However, when we start injecting steam, you can see the curves here start to have a shape, and we get the steam moving across, and eventually we reach steam temperatures also in the sand zone down below. And this is the perfect condition we want for thermal treatment. We want to reach boiling points from top to bottom so that the DNAPL cannot basically hide there at a lower temperature. If we hadn't had the steam, we would have had this red curve, and we could have had some untreated DNAPL at the base. So again, combine steam with conductive heating, and then you have a more robust solution. So get ready for your questions. Here's the final slide. In summary, steam can be used on its own for more permeable sites. We say about 1 Darcy, sometimes a little bit lower, is the lower limit of permeability. We need to have a fine sand or more permeable than that. If you're into silts and clays, it's typically too tight for steam to be cost effective. Then the second application, steam assisting electrical heating methods such as ISTD or electrical resistance heating is a really good combination where we can get more benefit than from one technology. And often it's actually cheaper, even though it sounds like it would be two different technologies would be expensive. But because you use the proper heating technology for the geology, it can be more cost effective than trying just one method. And most of all, it can be successful, where sometimes the single technologies cannot. So the pressure cycling I talked about is key to get high efficiency out of a steam project, especially if you have clay lenses and layers that you also would like to get mass out of. You have to know how to do the pressure cycling. And then as my wrap-up comment, basically it's not difficult to rent a boiler and build some wellheads and put the steam in the ground, but to do it right and to get a good treatment result, it is not simple. And we have all these lessons we learned from Udell and the Livermore crew, we still need to all remember. So thank you very much for listening. It's time for questions, and I'll just take